Yeah, we'll be talking about creating circularity for critical raw materials, and I'm very much already looking forward to the discussion later. I will talk about mainly three different things. After a brief introduction, I will talk about critical raw materials. What is that exactly? What are we talking about when we speak about critical raw materials? We'll talk about circularity issues throughout the periodic table. What kind of issues we have there, what's the current status of that, and of the circularity, and why that matters for critical raw materials. And then in the end, I will talk a little bit about a vision for circularity. Wasn't quite sure about the last part's title. Maybe it's not exactly a vision, but we'll get back to that. Yeah, I'm an industrial ecologist. So, well, what do we do in industrial ecology? We assess material and energy flows of the past, the present, and the future in order to identify the environmental impacts that those material flows have. And this is specifically relevant in times of the triple planetary crisis, where materials lead to climate change problems, biodiversity losses. I will not talk a lot about that today, and pollution issues. And we, of course, also want to change things. So it's very often a perspective of how can we make things a little bit better, at least, or sufficiently enough better so that planetary boundaries are met again. And, well, thanks to a lot of the work that has also been done here at Boku, we know that we are in a stockpiling society rather than actually a throwaway society. Extraction flows are increasing drastically, stocks are increasing even more rapidly, and waste flows are also on the rise. And today I'm going to talk mostly about this tiny little blue part here, which is sometimes forgotten and sometimes is a little bit problematic to make visible in the graphs, because obviously aggregates and asphalt and concrete and all these kinds of construction materials make up just so much more of the materials. But even within that blue part, we have huge differences, and I will talk about that later on. These impacts matter. We know that we should get to net zero carbon emissions for carbon dioxide. We're currently around 40 gigatons per year. We know that biodiversity loss is rapid and that global pollution with plastic waste, particulate matter, and other persistent chemicals are a global problem that we need to challenge. And large parts of those impacts are material related. This graph is from the Bend the Trend report from the International Resource Panel, and in red here highlighted are material-related issues for climate impacts. This is quite a bit, half of that maybe, but includes fossil resources directly. Particulate matter health impacts are also very relevant. Look at, for example, specifically here the non-metallic minerals, or in green, in yellow or orangish, the metals bars, which are very relevant here. The water stress and biodiversity issues, that's mostly an issue of biomass use. I will not talk a lot about this today. If we then specifically go into greenhouse gas emissions, we can go into a publication from Lambin colleagues where they worked on disaggregating the global carbon emissions. Now this is greenhouse gas emissions overall, so therefore it's about 60 gigatons in 2018, and disaggregated first into those mega sectors: energy sector, industry, agriculture, forestry, and other land use, transport sector, and the buildings sector. But of course, well, very often electricity and heat, that's not necessarily a demand for itself, but we use that for other sectors, so we can disaggregate that further. And this list is quite extensive. Yeah, I mean, you might not be able to see everything of that, but therefore I have highlighted the most relevant ones for you. And it strikes that on the fourth position already comes metals. So about 8%, some statistics say 9%, some statistics say 7%, depends a little bit on how exactly you count. But let's say 8% of the global greenhouse gas emissions come because we mine metals, we process metals, and that does not include chemicals, that does not include wood, etc., but that means just metals, all through the periodic table. So therefore, if we want to get to net zero, we will have to tackle those 8% as well. And that will be quite a challenge. It will be specifically a challenge because these metals are so different. I work in my research all the way through the periodic table. And that's a variety. Probably you have seen such a periodic table. Maybe it's been a while. And sometimes it's difficult to recall what exactly each abbreviation was. Might have heard that a while ago, but of course, nobody really remembers all 60 of them. There's about 60 metals in the periodic table that are chemically stable, not radioactive, and all of them have an economic use. Every single one of them is used for some purpose, but they are very different. I'll just pick out one number, and that's the production volume. Within the same group, we have iron and we have osmium. For iron, we produce about 2 gigatons per year globally. 2 billion tons. For osmium, 1 ton. That's it. That fits under this desk if it was a full cube. Obviously it isn't, because it's mostly used as a catalyst, and therefore you want to have a lot of sulfur, so you don't make cubes out of osmium, but it's just 1 ton. So working on data which covers 9 orders of magnitude, that's a challenge. We just had this discussion earlier today, where sometimes some of the data is basically focused only on bulk materials, where you have a lot of the materials and not on those kind of specialty metals. In colors, you see one of the many options to deviate those 60 metals into different parts. You can talk about ferrous metals, and we're talking mostly about steel and alloying elements for steel. We can talk about non-ferrous metals. That's from anything from wires to semiconductors to lead in your starter battery for cars. We can talk about rare earths element. We'll talk a little bit about that later today. And then there's the rest. Sometimes that's called technology metals, sometimes that's called specialty metals. But mostly it's a basket where you throw in everything else, which doesn't fit into those mega categories. And in my research, I work on data which is related to all of them, and we'll have a look into that later on. But let's first look at those large materials. So these are historic production data from iron and steel until like 2015 or something like that. And then projections into the future, estimations of how much of those materials we really need in 2030, 2050, 2100. So in a few decades. 2030 actually isn't that far away. You see also this rapid increase for both between 2000 and 2015, that's China. As for a lot of the materials, also construction materials, we see the huge China effect, which is just increased capacities for production. Half of the production of steel is happening in China. Half the production of aluminum globally is happening in China. So therefore, this is a huge of this more recent increase has happened in China recently. But we also see that this is a continuous growth. And if we think back about those 8% of the global greenhouse gas emissions that come back to the metals, well, these will make an impact. Steel, that's about 5% of global greenhouse gas emissions. Aluminum, 1.5%. So these are, of course, the 2 largest parts. Then there's copper, and then there's all the 60 others. So it adds up to the 9% overall. And of course, all of these will have to decarbonize if we talk about that. And the demands for the others, here summarized in a work from Takuma Watari and colleagues, is also on the rise. Equal estimations, in this case for 2030 and 2050 only. Sometimes for these specialty metals, it becomes a little bit problematic and complicated to make estimations for a few decades into the future. You see, therefore, also the estimates go, well, maybe even further apart as they were for iron and aluminum. But these are drastically increasing. And here you already see this separation. Some of these metals, coincidentally, it was all on the right, I'm not sure if this was intended by the authors, but coincidentally, all of these on the right are here in red critical or even critical and strategic raw materials. I'll get back to those two terms. And all of them on the left were not critical materials according to the EU definition. And one colleague from Tutzing in southern Bavaria nicely said last year, we can defossilize the economy, but we can't demetallize it. So working without metal stocks will be impossible. And a lot of the technologies that we rely on for decarbonization or defossilization, they rely on a lot of these technology metals or specialty metals. Now that brings me directly to this term of critical raw materials. What exactly is that? First part. Then we'll talk second part about the circularity issues. So a first important part is there's different conceptions of critical raw materials. And I'll talk about a few of them. I will mostly talk about the EU definition. But the very important is that some definitions work with critical raw materials lists. That means a material is either critical or it's not. Which is good if you want to do policy recommendations, which is good if you want to do laws or regulations, because then it's clear you're either on the list or you're not. But it's not very good if you want to measure progress, or it's not very good if you want to make decision support, what you can do or how to improve something, because if you're still on the list after your measure, what have you gotten? So therefore, these lists are very often on a policy level. EU criticality lists, US criticality lists, etc. But there exists also this other perspective that critical raw materials have an aspect or a grade of criticality. So therefore we can differentiate between those on the list criticality assessments, which have thresholds, and those gradual measurements of, for example, specifically supply risk assessments, which also companies can use in order to identify where are the pitfalls, where should we improve, and how can we improve. The second prephase or early notice is that criticality assessments should have something like a risk perspective. And in risk assessments, we work with these two terms of likelihood of an event and severity or damage caused by this event. And something is very high risk if it's both likely and problematic if the event happens. So of course, if you're in a flooding zone, or just coming from southern Bavaria last week, was very problematic to get from A to B. Apparently here in Vienna it was much easier. If something is in an area where there's frequent flooding, but there's no houses, well, where's the risk? If it's an area where there's a lot of houses, a lot of people living, but flooding events happen just very rarely, also it might not be an issue. But if both things come together, then you need to make protection measurements. And with criticality assessments, it's quite similar, but a very different logic. The problem is getting the supply. So it's a very supply-oriented assessment. We want to gain the materials that are required for the economy. And sometimes maybe you can even question whether these are really required for the economy, but then this is then the socioeconomic part of that. In many regards, this should be an assessment of a supply risk in terms of a likelihood of a supply disruption and a vulnerability assessment in terms of what happens if that supply disruption actually really happens. And you can see from the terminology that, well, this is common for criticality assessment, that they call this a supply risk, but actually in the terminology of ISO risk assessments, this is not risk, it's just a likelihood assessment. So when people talk about supply risks, what they mean is likelihood of supply disruptions. It does not mean that it would be a problem. Maybe this is a highly uncertain supply of a material which you don't need. Well, then why should you care? So that is an assessment result that could happen if the material is just down here in this corner. So increasing criticality should be something that's up in that corner. There are criticality assessments which you just use one dimension, which don't use this matrix style assessment. There are criticality assessments which use more dimensions, 3 dimensions, 4 dimensions. You will find that in the literature. But I will talk mostly about these two dimensions and this matrix style of an assessment. Now, why is this relevant also right now? So the European Commission has very rapidly gone through a process of going through a critical raw materials assessment in terms of a Critical Raw Materials Act. So in 2011, there was the first criticality assessment, and then every 3 years there came a new criticality assessment, but not a lot of policy followed with that. But at the end of 2022, actually, the European Commission, under the von der Leyen EU government or EU Commission, they started the process publicly to get feedback on a potential Critical Raw Materials Act. And now, 1.5 years later already, it's in force. If we compare that to other EU legislations, which go through a lot of multiple reiterations, this is very fast. So the first draft was just out in March last year, and the trilogue preliminary agreement was in November already, and then in March 2024, it was accepted, and now it's in force for 2 weeks. So very, very recent. And what does this Critical Raw Materials Act actually say? Well, it first of all gets you targets. So these are EU-wide general bulk targets. We want to get 10% of the demand for critical raw materials, to be more precise, strategic raw materials, we'll get to that, from EU sources. 10% overall, at least. So 10% of the EU demand shall be met from domestic production. 40% from domestic processing. So of course we know, well, for some materials we just don't have any resources in the ground, we don't have any geological reserves, therefore we need to bank on imports, but we would like to process them here in order to gain more of the value chain. And 25 of the demand shall be met by domestic recycling. This is interesting. In the initial draft, it was just 15%. And then throughout the trilogue process, all of a sudden it was 25%. So they got more ambitious, not less ambitious, which we also sometimes have in this trilogue process. Then there's strategic and critical raw materials. I'll get to that in the next slide. And the question is, what exactly do you want to do? Well, the one large part is strategic projects. So there's a lot about like permitting processes, how strategic permitting for mining operations, quarrying, as well as recycling facilities will happen. I was expecting that this whole idea would fail for the strategic projects and that member states would be much more reluctant, that the EU actually dictates how permitting processes work in member states, but apparently it was not an issue. Or maybe I got it wrong in the beginning. And there's some information on circularity and actually also environmental footprint. I will not talk about that. And then there's a lot of risk monitoring and strategic partnerships and that kind of things. So in Annex 2 of the Critical Raw Materials Act, it defines how the EU Commission, and therefore the whole European Union, shall define critical raw materials. And it's this nicely or weirdly looking graph, which combines information on whether materials are substitutable, whether they come from important sectors in the European economy, or whether they are used in those, rather to say, whether the supply is very concentrated, very often China, but not always, and whether we have some recycling on that. And it funnels into two benchmarks, so to speak, supply risk and economic importance. They are those two dimensions that we just saw. So the European Commission talks about economic importance when they mean vulnerability. And they also talk about supply risk. If there is an Annex 2, there probably is an Annex 1. And that Annex 1 says that there are also strategic raw materials. And those strategic raw materials are defined by materials where there's a high demand increase due to strategic sectors. Also, it defines that strategic raw materials need to have a high production scale and a low reserve to production ratio, which is actually interesting because in the criticality assessment, there was no information about geology, no information about reserves or scarcity of a material. It was just trading. Now, in the strategic raw materials, we need a lot. We need it for strategic sectors, and there isn't much, basically. But there's no quantitative public information about how exactly that happened and how the EU Commission came up with a list of critical raw materials then. It even came up with a proposal, and then member states said, oh, actually, we would like to have aluminum on that list as well. So therefore, and they said, oh, actually, it's not just natural graphite, it's synthetic graphite as well. So it should also be on the list of strategic raw materials. So they expanded those kinds of assessments at all. And the one thing that they did, and I personally think this is a huge flaw because it undermines terminology, they said, well, every strategic raw material is automatically also a critical raw material. So they have this very, they have this very neatly aligned, harmonized since 2017 assessment, but they don't follow it. Because if it's a strategic raw material, then skip that and put it on the list. And that happened. Copper and nickel, we'll get back to that, why exactly? They are strategic raw materials, although they shouldn't be critical raw materials. So therefore, they are now on the critical raw materials list. All accounts count for them as well. But, well, actually, there is no supply risk for those. Or at least not according to the EU framework. Why is that important? So these are the strategic sectors that the EU Commission looks at. Lithium-ion batteries, all the way to aerospace, aircraft, space, drones, a lot of automation, additive manufacturing, a lot of energy technologies, low-carbon industry technologies, digitalization, and that kind of thing. So quite a range, obviously. And these sectors are on the rise. They are drastically rising. And the JRC, Joint Research Center of the European Commission, or European Union, has assessed the amount of materials that we would need for these compared to how much of that we produce currently. So they assess that for lithium, graphite, cobalt, nickel, etc., we need much more potentially in the future. You can recall from the names, probably it's got something to do with lithium-ion batteries, than we currently produce globally, just from these future technologies that have been defined beforehand. And if they are then therefore important for these sectors, they will be defined as critical raw materials. And this is the official, I made a graph, but this is the official data for the criticality matrix. And you see all that are in this upper threshold are called critical raw materials. And nickel and cobalt don't actually have supply risks, therefore they shouldn't be, but they are still on the list because they are strategic raw materials. They are the only strategic raw materials of a list of 15 that have not gotten above the threshold. You also see, well, actually, most of them are above the threshold, this dashed line, of economic importance anyway. So it's not very important where you land on this economic importance, because most of the time, most of the materials are above that threshold anyways. And you can't actually do a lot about this economic importance measurement, because basically the main important factor for the EU Commission to determine if a raw material is economically important or not is whether it's in the automobile industry or not. Because basically what they only look at is statistical data, what's the value added of the sectors where a material is used in. Well, we use tungsten only for machines and cars, and well, this is a large sector in the EU statistical data, therefore it is on the right side. So you can't really change that, because you will not change the applications, right? But you might be able to change the supply risks. So the most important part is whether a material is considered really having high supply risks or not. And this is something where the Critical Raw Materials Act also draws on to reduce potentially those supply risks, not reduce the economic importance of the materials. That wouldn't make sense. And those supply risks can be measured and they can be managed. These are the 10 in a variety of supply risk assessments, the 10 most used supply risks aspects. And I put a European flag everywhere where the European Commission in some of their assessments, either critical raw materials or strategic raw materials, has made an assessment of that material. They use concentration data. So how much concentrated is a market? They use the scarcity now also. Political instability is used, regulations are used, and then byproduct dependence on primary production is used. So basically recycling information. Demand growth is used, substitutability is used, and import dependence. The only two aspects that the European Commission doesn't look at is price volatility and byproduct dependence, because byproduct dependence, well, would be quite geological, and there's not a lot of mining happening in Europe anyways, except for a few metals. So these can be measured and managed, and specifically for the dependence on primary production, we can invest into recycling and we can invest into processing technology, and that's the largest part. So let's talk about those circularity issues. If we talk about circularity, as here in this case from a nice graph from Willi Haas and colleagues, we can talk about input cycling and output cycling. Of course, with these kinds of metals, we cannot bank on ecological cycling. Well, those geological cycles are very, very slow, and therefore this will probably not work out until from a battery that we throw into the environment, something magically all of a sudden, once again, a geological reserve emerges. That will not happen. So we will need to have a socio-economic cycling. If we really want to reduce supply risks, then we will have to look into input cycling, because we're interested in the material that is processed. It's not about the waste and how much of that we recycle. It's a question of how much can socioeconomic cycling replace those materials that we need. And we've had a look into this for a variety of metals in the periodic table to identify from those stocks throughout the economy how they behave. And I will make this very clearly from the example of aluminum. So in the beginning, there's bauxite mining. From this bauxite, you can make an aluminum rod alloy. This aluminum rod alloy might become a body in white for a car, and this car is used for a while, hopefully for a long time, hopefully very intensively. But at some point, it will become scrap. Now, the issue with aluminum is you can't get rid of alloying elements. So therefore, very often, after some time, this actually becomes a motor block. So it becomes cast aluminum, and you cannot go back. You cannot make a rod aluminum out of cast aluminum because the silicon content is way too high. Therefore, this is a one-way route, so it's a dead end. And at some point you will be stuck with a lot of cast aluminum, and you cannot really close the cycle overall. So at some point, all of these materials will be lost somehow. And we wanted to quantify how long that takes. How many years pass between mining and some kind of loss? It can be other sorts of losses into the environment, etc., or into some landfill. And we did that for 61 metals. So once again, these are these 4 big types. So now put rare earth elements into the group of specialty metals. For ferrous metals, it looks like this. So you start with 1 kilogram. Imagine you could flag 1 kilogram of iron that has been somehow magically mined, and then all these atoms, they get flagged, and then you pursue them for 200 years. course, this is just a statistical example, just the modeling. What would happen with these atoms of 1 kilogram of iron and ferrous elements? Well, you see, after 100 years or so, basically there's just iron left, and the rest is somewhat lost. But even for iron, after 200 years, there's a lot remaining. And you lose that mostly, for example, in waste management due to some thermodynamic losses during steel remelting. Ferrous metals, their steel recycling obviously is the most important process. This is how the graph looks for specialty metals. After 100 years, there's hardly anything left. And the most important ones that we lose is either already during the production, so during mining and separation from host metals, or during the use phase, because the materials are not collected at all. There's no waste that we could recycle. So if we calculate that, yes, gold, iron, aluminum, nickel, copper, silver, platinum, they're fine. Fine-ish. Of course, they can still be better, but basically they're at maybe a few decades, 1 or 2 centuries, as a statistical average. For half of the metals that we looked at, it was 10 years or less. So that would mean that we would have to mine the same amount of materials every 10 years again as a statistical average, which of course is not what we would like to have. It's very far away from being cycled. And you could put it in this periodic table once again and compare that, for example, with the recycled content, where the European Commission looks at, or with this end-of-life recycling rate, so the output cycling. So from the waste, how much of that material is cycled. And everything that is reddish or yellowish that you see here, that's not what we want to have. This is even 10 years shows up here as yellow, because it's better than those with just 1 year or even shorter. So that's an issue. And it occurs all the way throughout those specialty metals. Iron, gold, aluminum, lead, nickel, copper, it's all somewhat okay-ish. But the others are very problematic. And if we come back then to the criticality assessment method, it matters a lot for the European assessment. Because this here above, this neatly looking calculation formula, that's how the EU Commission calculates their supply risk assessment. They multiply 3 factors. Starting from the right, substitution. Is there a substitute or not that you can have on the market? And then already the end-of-life recycling input rate. So the input cycling, socioeconomic input cycling of each metal or each critical raw material. And then there's some calculation of global or European sourcing in terms of concentration and political stability of those countries that you source them from. So this is, in many regards, the most influential factor. If there is a lot of secondary raw material that's available that you can have, then it's not going to be a critical raw material. It's going under the threshold. And the highest values that the Commission found was for lead, 38%. That's your car batteries. They're very well recycled. Copper, rhenium, this is mainly industry applications, so therefore you purchase and you use catalysts in their solvent. They go to a specified recycler and you get them back. So this is not a customer product. Tungsten, zinc. There's a very nice article why exactly this 43% number is wrong. It shouldn't have been used by the European Commission. Actually, it's 11%. It's way worse. And then zinc would have been a critical raw material, but it's not, because the European Commission doesn't acknowledge that they made a mistake in that regard. Aluminum, iron, tin, cadmium, molybdenum, all of them have 30% or more in terms of input socioeconomic cycling, those end-of-life recycling input rate. And that directly reduces all the factors that they get. So the question is, how do we get this far end, which I cut off here, to higher numbers? And there comes this vision for circularity. The first thing that we need, that's typical scientific answer, better data. we have, and Jens Rieck and colleagues have worked quite a bit on how do we match a metal production to specific applications. And the European Commission does that as well. They use information on which sectors or which applications is a material used in order to, for example, identify whether there is a substitute or not. Therefore, they need to know where it is actually used in. But we need to be more precise in that regard. A metal is used for a specific material. And this material then becomes part of a component. And this component becomes part of a larger product. And then you will use it. Sometimes this is very straightforward. Sometimes it's very a lengthy course where maybe there's a component and a component and a component could be very like multi-parts, but we should be more precise in what type of a material is it used, why does that matter for a component. This component actually has some kind of a physical function, and then it goes into a product where it fulfills an economic or social function. And it matters for our strategies. So all of these recycling or remanufacturing strategies, therefore we need to identify whether this is actually a homogeneous material. Is it a material that needs to be pure, or is it a material that needs to follow a very specific composition? It doesn't always have to be a pure material to be high quality. Are these components and products disassemblable so that we can separate again the different materials in the waste streams? And what are the contaminating elements? So, for example, copper in steel is an issue. Copper content in steel is rising in Europe and in Asia and in the US, everywhere, and becomes an issue for steel recycling. But of course, copper contamination is not an issue for aluminum that much. So we need to be very specific about what kind of material are we talking about. And steel and aluminum are both used in cars. So it's not about copper in cars, it's copper about copper in specific materials. And you can also make this example with batteries. So lithium and cobalt are part of a cathode active material. This cathode active material is part of a battery. A battery has a very heterogeneous composition, but the cathode active material has a homogeneous composition. But if this lithium-ion battery is used in an electric vehicle, or if this lithium-ion battery is used in your in-ear small microphones or headphones, Apple AirPods, etc., then of course this is a very different question to recycle those and collect these, etc. So, and both of that is lithium-ion batteries. So the R strategies matter how we actually model those kinds of materials and components. And this modeling can then also be more specific. So we do have these products, the production of raw materials, which are then fabricated into components, which are then manufactured into products. Then they are hopefully for a long time in the use phase. So we need to make sure that this use phase uses those stocks very intensively so that we can actually reduce the amount of copper or cobalt or lithium that we would need for all these kinds of electric car vehicle batteries. And of course, they can be repaired. Then the materials need to be collected. Very often this is an issue because, well, there is no specific collection for a variety of the smaller products and variety of materials that are in small components available. And then they need to be more separated. We're working partially on that, like disassembling requirements, also in battery regulation on EU level. And then they need to be recycled. And in this recycling process, well, we would like to have information not only about how efficient is steel recycling for steel, but also how efficient is steel recycling for contaminants. Can we get them out? Do they persist in the materials? One example would be that, for example, zinc that we use for galvanized steel, well, quite a bit of that we can recycle from EAF dust. So from electric arc furnaces, the zinc goes into the dust, and there we can get it back. With many other materials, they are much more problematic. So we need to be very specific about recycling efficiencies for minor metals, which they were actually not targeted for. And that, of course, requires like a lot of process knowledge, thermodynamic modeling, chemical engineering, or metallurgical engineering. Sometimes the problem occurs that these materials become of less and less quality. I just mentioned copper. I mentioned the aluminum case as well. There, the materials go through this cycle, and maybe for a lot of reasons, the quality of the material is deteriorated. Materials wastes are mixed with each other. Alloying elements are maybe lost throughout the process. And all of that increases the demand for virgin material once again. So therefore, we need to look at aspects of downcycling. And I would have a few examples of that later on, maybe in the discussion. Then if we want to do this recycling part, it's important that we have the facilities. So the EU Commission would like to have 25% of the production capacity for strategic raw materials in Europe. Well, what if we don't even have primary production capacity for those materials? Why should we have then recycling capacities? So this will be a challenge. Luckily, this is just a bulk parameter, so they can do that with copper and then they're done. They have defined copper as a strategic raw material. That makes a lot of the bulk material calculations for them easy, because there they are already at 50% plus. So, well, just calculate that in and they were done. But if we go into these more minor metals, I just mentioned copper here. That's an issue in iron recycling. But what about the other metals? We need lead and zinc metallurgy. This is a collector for a lot of the materials. And we need to define better pathways there to get from one metal to the other and selectively extract those kinds of contaminations maybe that we have gotten into them unintendedly throughout our waste collection systems, and we need to get them back. So we will see a huge shift from pyrometallurgical recycling systems to hydrometallurgical systems, but they need to be very specific for each of the waste material streams, and they will need to know a lot about the information about how the wastes actually are composed, because they are very selective to variances in their composition. So all parts of this metal wheel, as Markus Reuter has defined that, are required for a functional circular economy of metals. So these types of downcycling effects. A few examples. So we already talked about nickel a little bit, which is a strategic raw material. Nickel, for example, the main issue for nickel recycling is that nickel sometimes gets diluted into carbon steel. So we actually use it mostly, we also use it for batteries nowadays, but we use it mostly for stainless steel. And some parts of the stainless steel always gets collected with carbon steels together, and then it's recycled as carbon steel, and then nickel is basically just a filler material in carbon steels, where it doesn't make any sense to have it there. But it's not a contaminant, so it doesn't deteriorate the material quality, so we will accept that. And obviously, because this carbon steel production is so much larger than the stainless steel production, it doesn't matter that much metallurgically. But it matters circularity-wise. It matters for the nickel steel cycle. Contamination, we already talked about the contamination with copper. Lack of demand, that's an issue with gallium, for example. Gallium appears in my statistics as a very short-lived material. It appears as a very high supply risk material in the EU Commission assessment, but only 10% of aluminum producers worldwide have a gallium separation facility because the market is not there. We could produce 10 times as much gallium from primary sources than we do. Gallium was produced in Germany for a long time, one of the three largest producers worldwide. Well, the Chinese got it out of the market because the prices were so low. Well, they could start it again if the prices were higher. And they could recycle if the prices were higher. And then the last one is design-induced. Well, sometimes thin films recycling will always be tricky. So indium, that's a big issue. Very often in your smartphones or your laptops for thin films, indium tin oxide, transparent conductive material. Well, you can't get indium out back from your smartphone. You will not recycle that. It's just so few of the material. That's not valuable, and that's thermodynamically really complicated. but that's the main application. So a checklist. We need to improve our composition knowledge. We need to reduce global stock growth by using our stocks more efficiently. We need to improve end-of-life waste collection, so more separate bins. Yes, this will be laborsome, but actually it's important to be more precise where each waste material stream goes into, and if we have more homogeneous materials and more homogeneous waste streams, then all of these metallurgical processes will be just so much easier. We need research and development on selective recycling processes. This is sometimes very difficult to identify exactly in which order the various materials need to be separated during hydrometallurgical process routes. We need to avoid those kinds of downcycling phenomena, which will also be tricky, in order to increase the recyclate qualities so that we can use them again and again and again. So, for example, you make an aluminum car body out of an aluminum car body once again. There's a lot of research and industry action in this regard currently. And the last one is, well, what will also happen is, well, making primary materials more expensive. So carbon taxes help, because for a lot of materials, they also have significant carbon emissions, just as we saw. If those 9% or 8% of the global greenhouse gas emissions become more expensive, well then there's an automatic shift towards making recyclates more economically viable. So, as a summary slide, and I will just keep this open, we have huge environmental impacts from metals. Critical raw materials should be defined as those which have high supply risk and high vulnerability, both together. There are 32 true critical raw materials currently in the EU plus nickel and copper, which are strategic raw materials, but don't actually match the threshold for supply risks. And if we can increase the recycling content, then this is very important because it's a core measure to decrease the supply risks in the Critical Raw Materials Act and in the EU measurement. Also in the US measurement, you can do that analogously. And doing that, just from this little bit of a checklist, will require transdisciplinary and interdisciplinary efforts, because it's there's no silver bullet. There's a lot of small bits and pieces that we can work on in order to get those numbers to higher circularity. With that, thank you, and I'm very much looking forward to the discussion.
Thank you very much for the great talk. I'm just moderating.
Dominic.
Okay, so thanks for the amazing talk. I'll be moderating the discussion. So who's brave and has a first question to get the ball rolling? Yes, please.
The mic, please.
Oh, yeah. I have one question about maybe the connection between sort of the climate motivation we had at the beginning about these emissions and then the circularity recycling. Because all of this recycling, especially if you now talk about getting contaminants out of the metals, sounds also very intense process that probably requires a lot of energy and can lead to emissions as well. Is it still sort of necessarily for all of them better to go through this intense process of recycling and contaminants, or do you get into a territory where for some of these metals maybe that's then doesn't have like a supply benefit, but you sort of lose a lot of the climate benefit?
Yeah. So, yes, theoretically, there is always an optimal recycling rate, depending on how strongly the environmental impacts, or for example, energy impacts requirements are increasing, the higher of a recycling rate you get. So in terms of output circularity, the last 10% getting from 85% to 95% recycling rate will require a lot more energy than getting from 5% to 15%, obviously, because you do the easy parts first. For most metals, we're not there. For lead, one could discuss that. If we are already at 83%, yeah, increasing that to 88% or so will be laborsome, and it will probably also become very problematic because we might actually use less starter batteries with electric cars or smaller ones or so. So that market actually might change, and then other LED applications become more example. But as long as, for example, the collection rates for these metals are so low, then we're not at that point. We could calculate that, and it might be very, very different. There's one more thing to keep in mind. Many of the greenhouse gas emissions for primary production are not energy related. For example, steel, a lot of the emissions comes from coking coal being oxidized to carbon dioxide, so coking coal is a reduction agent for the production. We hopefully will replace that maybe partially or fully with hydrogen or something similar, so that you have a non-carbon-based reduction agent. In aluminum case, for example, yeah, it's a lot of energy requirement, but also there you need to do once you need to do the reduction from oxides to the metal, and as long as you keep them in the metal state and just some alloys, then the recycling will be so much less energy intensive. Therefore, the gap that we can get is quite large.
Great, thanks. Yes?
Thank you for breaking the ice. It's usually me who does that. Thank you very much for your talk. I feel like it was a crash course in these materials, and was very good. I want, on the one hand, to pick up on your last point. Do you have an estimate when the energy system becomes based on renewable energy sources? How much of the 8% would be not an issue anymore? That is the one part. The other part, I mean, as you describe it, it's a very liberal understanding of we can use all kind of materials as we want them. If you would think about in a different way, to say, is there a way of reducing the number of elements? Is there a way of going into a sufficiency direction in that field? What would be the option space then? Yeah. Mm-hmm. Is there a simple solution to say there are certain areas that are not so beneficial but make a big part of the problem, and there may be other parts that are less problematic but are very beneficial? Is something like that a kind of perspective to look at this?
Mm-hmm. All right. So 2 parts of the question. I'll do the first one first. So if we decarbonize the energy system, if we just take the 2 examples of iron and aluminum, it's a completely different answer. For iron, 80 to 90% of the greenhouse gas emissions is process related. So if we decarbonize the energy system, then yes, EAF steel will be even better, so recycled steel. But basically for primary steel, not a lot changes, because there most of the energy comes from maybe some gas, natural gas that's sometimes fueled specifically in the US. But most of the emissions come from coking coal. For aluminum, 90% of the emissions come from the energy system, specifically for the electricity. So if we decarbonize the electricity, there it matters a lot. So if iron is 5% of the greenhouse gas from the 9% that we're looking for, and aluminum is 1.5%, we might not be able to do a lot with the 5%, that definitely remains, and with aluminum we might be able to reduce this 1.5% to 0.15%, which is of course quite a game changer. For the other metals it varies quite differently, quite separately. Regarding the sufficiency question, so we did one model, actually Takuma Watari was the lead author there, where we looked at global metal use targets in line with 2 degrees Celsius. And we had this underlying effect or underlying assumption that all of the metals have their fair share in decarbonizing. So they would also get a budget, the same budget for each of the metals, which of course is an assumption. And there we said, as a key result, the per capita stocks that we have in high-income countries would not be able to be rolled out globally, even if we have higher circularity ambitions, even if we have some level of green hydrogen that's being used for steel production, even if we decarbonize a little bit the aluminum sector, just the sheer amounts of materials that we use for getting all world regions to this high per capita stocks would be too much. Therefore, we'd have to reduce the stocks, and we would have to have much higher secondary raw material use in those circles that we have. That would be, however, of course, every material getting the same share, which I'm not a big fan of, actually, now a few years after the publication, because some of these materials are very relevant for energy transition materials and energy transition technologies. So it might be very valuable to foster these and still use that, manage the supply risks, because their benefits on substituting fossil fuels elsewhere is just so high. And with electric cars, that's definitely the case. So the benefits in terms of less fossil fuel production, less oil and gas production that we have. Can I help you?
No, I don't think I can be helped anymore.
The benefits that we have there are just so high that we should be able to manage those minor metals. With iron, aluminum, copper, maybe that's a different story, but with the minor ones, the environmental impacts are by no means a comparison to the large decarbonization efforts.
Because we have a question in the chat. Yeah. There you go. Oh wow, that's a pretty long one.
All right.
Yeah.
Hello, everyone online again.
Yes, great that we have people online still with us.
So when I read that out, or?
Yes, so if we have, do we have a question in the room straight away? Because otherwise we can, is that a hand or not? Okay, okay, that's good. So I will just, thanks for the question from the chat, from Luis. I will just read it out. I would have a question regarding the supply risk indicator that is a function of the end-of-life recycling input rate. You said that there were some downcycling issues, into particular urban deposit flows. How would you improve the end-of-life recycling input rate factor to encompass the potential recycled mass? Is there a potential metric that could estimate the amount of recyclable materials of a particular deposit made of products, components, and materials? So I guess the summary is the potentials, are they assessed to some extent?
So the Commission assessment looks only at, let's say, the recent past. So typically they would like to do a 5-year average, for example, for the trading data for the recent years. So the 2023 assessment was based on trade data for 2016 to 2020, actually. So it's not even very current. With the recycling data, we're happy to get any number. Let's be honest, because getting a global estimate for the end-of-life recycling input rate for, say, gallium, okay, well, there you know it's 0%, for zinc is really challenging, simply because the markets are so different, or for antimony or something like that. So all these kinds of minor metals where you know it's definitely not 0%, but it's also definitely not 60%, but somewhere in between. And you're very happy with getting the number, maybe that's even 5 to 10 years old, but it's actually from a decent data source. That's the European Commission perspective. In terms of a potential, well, of course, yeah, we could look into each of the various materials and estimate what we as scientific or maybe industry experts say, oh, this is an application where we could recycle the material, and we do have a recycling technology if, say, the collection mechanism is there, and then do a dynamic MFA, so dynamic material flow analysis, in order to estimate how much in 10 years this secondary raw material could substitute the material demand of that time at that. But that's much more laborious, and it's much more difficult to get it in a harmonized way for 60 plus metals, or 80 raw materials as in the European Commission assessment, because that doesn't look only at metals but also at other materials. And therefore this harmonization and comparability is quite important, and I would say this potential recyclable materials is more for like a detailed look into one of the material streams.
And I would probably add that these kind of assessments only look at kind of a theoretical lifetime, and we don't really know actual lifetimes of things for many products.
Yes.
And we always then have the problem of economics, because prices drive a lot of these developments, not just like physical availability in some waste bin. So
absolutely.
And then there's this joint problem with what does potential even mean.
Yeah. And I mean, also in terms of the downcycling, because the downcycling issues is mentioned in that. So downcycling is also recycling, but downcycling comes with a quality loss. So one could say, well, should we devalue this quality loss a little bit and say, well, we could adapt our recycling statistic in that regard. The EU Commission only looks at recycling, as long as it's not like some kind of backfilling or something, which would then really downcycling, because it's definitely terminal. But anything, even if it's a low value application, is still recycling.
Any questions from the group? Yeah? I will then return to the chat, but let's alternate a little bit. You want? No?
So for another question, Jakob from PIC. I have a question. You had this like key publication on the lifetimes of the metals. I was wondering if this is reflected anywhere also as sort of a target, because it seems that would be also interesting to look at targeting, maybe getting those lifetimes up a bit. But then what we saw from these EU directives, it could also, with the targets they have set, it would actually probably be counterproductive. Because if you now start increasing these lifetimes and work on measures that do that, you suddenly reduce the outflows, and then the target that you're measuring goes down. So if you then look at sort of, because you have less material to recycle and into these input flows, so is this lifetime, like extending the lifetime of these materials, is this somehow also being addressed as part of this policy, or?
I'm not sure if I got the question right.
Okay. Maybe I also
understood it wrong. Can you rephrase it with your
We try to improve the lifetimes of products, which is actually a high-level strategy for circularity.
Yes.
You actually decrease end-of-life flows.
Yes.
Because stuff is in use longer.
Yeah.
So you might actually have less recycling happening because you have less end-of-life materials. And I think the question is...
And now the question is how that relates to my decades or 10 years lifetime.
Because that seems the output of the research, but then in the EU part on the targets, we're just focusing on this recycling. So this is our target. Might we do something, counterproductive there, because we are totally ignoring this lifetime issue?
So, in the EU Commission report, the end-of-life recycling input rate is used. Ideally, if available for the EU, if not, then on a global scale. If we reduce the amount of waste that we can recycle after end-of-life wastes, we're not talking about fabrication wastes, end-of-life wastes, there is less available, so potentially this number might increase. But if we extend the product lifetimes, we might also decrease the amount of material that we need. So therefore, we might reduce the recycling, but we also might reduce the full material requirements. Therefore, this effect might not be as strong as we could imagine, ideally. But of course, there's also rebound effects, etc., which might be very difficult then to estimate beforehand. But yeah, that's a potential downside of simpler to calculate indicators, sure.
But I would add that the use of an input recycling rate is actually a really good move in
Yeah.
here. I
I
was
agree.
very positively surprised because that opens up a lot of options, isn't it? If you decrease demand, you basically automatically increase input recycling. So there is different ways of looking at that.
You see there clearly that the criticality assessments is an exercise on the EU level, is an exercise done by DG Grow, so by the, so to speak, economy ministry. So it's not from the DG Environment. So therefore, this is clear that they look at how can we make sure that the European economy gets the raw materials that it desires. It's not a waste regulation. I'm not going to say about which material it was, but during one of the discussions, it was quite interesting that they said, oh, this material now all of a sudden becomes a critical raw material. Prepare for backlash from DG Environment, because it was a toxic material that all of a sudden is economically very important. So therefore, well, there's some conflicts in between different ministries.
Edgar Hertwig from NTNU. Thanks for a very interesting presentation. Of course, I've followed the debate for almost 2 decades. It's quite interesting to see how it has developed. I think this initially the concern about critical raw materials came from Asia, right? The Japan, I think, which generally doesn't have mines, right, and therefore a big problem with depending on external resources for everything, but also China early on sort of recognized the importance and acted strategically to secure its own supply. And now we are sort of a latecomer to the game. I feel very much that's the case. And what you describe, I feel like there is these two strategic and critical material definitions. You have one sort of schematic process, which is scientific or pseudo-scientific, and then you have a more political process where industries say what is strategically important for them, right? And then we define specific industries as strategic in their products. And so the interesting thing is that this more schematic assessment is based on static information, right? It's based on information in the specific point in time, whereas a lot of the components of the more like political process are exactly, oh, we will need to make more batteries, right? They become a much more important part of our economy. Therefore, we need to secure the supply of the resources we need for those batteries. So there is actually, in some way, the real value, I think, to this more strategic or political process. And that is interesting to see, actually. So it's just a comment from my side. And I wonder how have you looked at this, like the future demand for the energy transition, these questions where we say, well, you know, we need more EVs, we'll need more solar panels and LED lamps and stuff like that, and what are the materials that we need for that?
Yeah. So, of course, I talked a lot about the political way of doing criticality assessments. Yes, there's a scientific paper behind that basically describes how the process works on it from Blanghini and colleagues from 2017. Ever since then, the method hasn't really changed. But there's also other scientific approaches towards doing supply risk assessments, specifically those. For example, we looked a lot into supply risk assessments for energy technologies. I looked at lithium-ion batteries, how that changes from one material to the other. We looked at thin film photovoltaics, whether this actually matters between the various discussed technologies, and more recently we already published a paper on photoelectric chemical water splitting, so alternative ways of producing green hydrogen, artificial leaf more or less. And there we specifically also said, okay, well, this is a technology that's definitely not market ready, so there will be quite some time to develop that, so we need to use indicators that are much more future oriented. So we work with, for example, reserves instead of actual production data in this future perspective, and then put this in comparison. And there's other assessments as well, where, for example, the future technology demand plays a much higher role in terms of quantifying whether there's actually a supply-demand gap. I mean, because there's always two parts, right? You can have a supply-demand gap if the supply reduces, but you can also have a supply-demand gap if the demand all of a sudden increases, and you can't keep up with that. So therefore, there are alternatives to that. I share your view that this current assessment of the EU is very recent past, so to speak, oriented, and not very future oriented, whereas the strategic at least has some components of that. One more note, you said 20 years. There's actually some very interesting reports and papers out there which go very far into the past and which have a very similar notion and very similar wording, and they also talk about strategic minerals, they also talk about criticality sometimes even of materials that are from the 50s or from the 70s all of a sudden, where you see, we've had this discussion beforehand, for example. But you can imagine that in the 50s this discussion was much less about China and much more about Russia. Or the Soviet Union.
Okay, yes.
Yeah, you had this one graph showing the life cycle of a metal consisting of different process stages, manufacturing stages, and what I'm specifically interested in are those losses. So each manufacturing process has been consisting of losses as well, and what is meant by those losses? Are those just quality losses, or are those losses that somehow are going into the nature, into ecosystems? And this would also be my second question. We have discussed greenhouse gas effects and how they contribute to climate change, but what about pollution? Can you probably say something about pollution also regarding to upcoming technologies, future technologies? What is their contribution to pollution? Yeah.
All right, so the first one, we have this, in this model, we had this very simplified way of looking at production, fabrication, manufacturing, use phase, waste management, collection, and then actually the recycling process. So very aggregated. And there we put this loss factor in there. Depending on which metal you look at, these losses are either irrelevant, because they're way less than 1% or something, or they are highly relevant. So I'll make one example, gallium once again. If only 10% of gallium producers have a gallium separation facility, well, where does it end up? Option one, it ends up in the aluminum. No, it doesn't. Or it ends up in the red mud. Yeah, it does. So you do have gallium concentration, still in orders of ppm, concentration in red mud, which is a byproduct waste material occurring during aluminum processing, very generally speaking. And it's a waste material that needs to be dumped somewhere. So you will never touch this again, and you will not get gallium back from that. And it's into the environment. That's definitely a loss, and it's a huge loss in terms of gallium. But there's also aspects of, for example, if iron is smelted, there's not a lot of loss. This is a highly efficient process, huge volumes, not a lot of surface processes, and so on. So once this iron actually enters pig iron stage and becomes steel, there's not a lot of processing waste for that. Of course, we do have also these metals like aluminum, which have huge cutting rests, so processing and fabrication waste that get remelted right away. So we also had this factor of processing waste that can be recycled at high quality, which always the aluminum industry uses to increase their inflow or input cycling rates, and say, well, we're so good, we have so much recycled material. Yeah, you produce that waste in the first day, and then you recycle it. It never actually touched any use phase. So please don't calculate that. But of course, it's nice to tweak your statistics in that regard. And there's last example. I already talked about indium. So if you have these thin films for indium tin oxide, you can imagine how that process works like. It's actually it's a process that works with indium sputtering onto this target, more or less. So you have a lot of losses onto the atmosphere around that product. That gets highly recycled, but of course it's also a highly inefficient, inherently a highly inefficient process. So therefore there will be quite a bit of losses, and that is actually a high source for indium contamination somewhere else. So this is one loss. So you see, depends quite a bit on which material you look at. Regarding the environmental question.
Sorry, can I just jump in? One thing you didn't mention, which is losses by design. So
true.
in the use phase, I guess...
My typical example is titanium. So the most frequent use for titanium is white paint, titanium dioxide. You will not recycle white paint because this is construction waste. In the end, at some point, you will not scratch this from the wall and get it back. Titanium dioxide is also in sun protection. Yeah, you will not get the titanium dioxide out of the ocean again. Probably not. So therefore, there are inherent dissipative uses, which for some metals are quite relevant. Of course, if you have a titanium medical device in your body, well, that can be recovered after the use phase. Yeah.
There is also stuff like brake pads.
Oh yeah.
Isn't it?
Yeah, there's a variety of examples.
Every bike has a brake pad. These are metals, and by definition they are dissipated because you brake, so you always lose material. And there is also, I talked to people who looked at all kinds of medical applications. So for example, if you do X-rays and things like that, sometimes you have to take this liquid to increase the Kontrastmittel.
Contrast agent.
Yeah, that's not really recycled. It goes down the drain. So I think if you look around, you will find a lot of examples where kind of small losses occur, which in the end lead to a loss of overall losses, a lot of overall losses.
Yeah. And that, of course, brings me then to the environmental question.
Yes.
Because there we then have to look into, okay, so do those elements matter if we emit them into the environment? Are they potentially toxic? Well, we have REACH and RoHS restrictions where we look partially in terms of are they toxic during use, but we also look into are they potentially toxic for the environment. So basically that's a chemical registration issue. And we would like to look more into like safe and sustainable by design. I think this is a nice overall concept brought up, so that in theory only chemicals that are safe for the environment will be actually allowed to be produced in large quantities by the industry. From the past, we have seen that sometimes we just know that 20 years too late, that it has been a problem. And of course, with all this PFAS problems, for example, this will be quite challenging for the industry. But there have been examples in the past where also the industry said, well, this will be terribly difficult to replace, and then all of a sudden 10 years later there's a solution. So let's find some creativity in that regard as well. Most of the metals, in many regards, if they are emitted to the environment, are non-toxic and not problematic. So therefore, they are then also probably not that much of a problem.
Yeah. My name is Hans-Peter Wieland, with Dominik, and I have actually 3 questions. Yeah, but
Dominik, you might have to help me then.
But
Right.
2 short one and one. I don't know. But the first thing is actually an observation. I don't know if I saw it correctly when you showed these strategic sectors. That list. I think the military was not part of it, right? You showed. There were some robots, some drones, things.
There's aerospace and defense is sometimes.
Okay. So it's hidden between those items.
If you need things for jet engines or so, then it might be very relevant.
Yeah, I was just wondering. Yeah.
Tanks typically don't show up.
Yeah. So that was the first. The second one is I was thinking. So what is your opinion on the possibilities or the options of digitalization for recycling. So, I mean, the problem of the collection and sorting and things like that. And we have now these new tools, I would say, like tracking things, Internet of the Things, or what is it called? Like all this new technology that's out there. I mean, there must be some ideas how to use that to manage the collection and sorting. Yeah,
I'll be able to answer that. Okay.
Yeah, exactly. This and the second question was because you always, well, I mean, the target or what is the goal, like increasing the recycling rate and extending the lifetime and things like that? I think that's pretty clear. So what is the goal, right? So I mean, it's complicated still, yeah. But the question then is what to do to reach that goal. I mean, from the perspective of let's call it policymaker. Yeah. So I mean, we talk about the European Union, we talk about the national level, all these different levels. So what can these decision makers actually do? And you just mentioned taxes, right? That was I've heard. So you said the carbon tax, so because then it's more expensive, the primary and so forth. But I was thinking, is there more? Is there more? Yeah. Because I think actually it's by changing the prices, you try to change the market for these products, and I think there must be more options to change the market than to the prices, right? So these are my questions.
Okay, thanks. So I think the first one we already covered. So the second question, digitalization. 2 parts. First part is sorting and separation technologies. It's amazing what's nowadays possible with high throughput sensors, partially also visual detection. So one example, by now you can put aluminum scrap through a process. You put multiple cameras on it, multiple lasers. You smelt the surface. Very briefly, you do an X-ray analysis of what this alloy is. You need to smelt the surface very briefly because aluminum has a lot of surface effects, so you don't want to actually measure the surface, you want to go a little bit below that. And then you identify what kind of alloy it is, and because probably the alloy is homogeneous within, so from one measurement you can be fine in terms of the composition of the material, and then you identify, okay, this has magnesium in it, it's got copper in it, it's got this in it mostly. So there's a variety of sorting options that you have, and you can just then do bits and pieces out of that. And you can do that in live with high volumes. This is amazing. This was not possible 10 years ago. So you would have to guess and do or do eddy currents and that kind of thing. So that wasn't very efficient in terms of separation. So it was more like we know where the scrap comes from, and therefore there's probably this alloy, and therefore we will sort it this way. Nowadays you can be, through digitalization and sensors and high throughput, you can be more efficient in that regard. Second part is product passports. So sometimes maybe even we will be able to identify exactly what the composition of this product is if there is a digital product passport. And there will be a lot of digital product passports if the legislation goes through. We do now have a battery passport as like the first version. So the EU battery regulation mandates that every battery that's put on the European market needs to have a battery passport, and that battery passport needs to state what kind of cathode active material is in there, what's the carbon footprint also of this battery, and how can this product be dismantled, and these kind of things. So therefore, also the waste sector gets a lot of information without any measurements. So then you can be sure, oh, this was with this battery produced 6 years ago from this producer, and I will put them together with all others from this producer, and that's fine. And you get this information just from reading the QR code that's printed for a long period of time on the product. As long as that's not damaged, that's going to be fine. So these two options that we have, and with these kinds of environmental footprint regulations, eco-design directives, which now go much more from energy efficiency to carbon footprint efficiency, we will probably see much more product groups where these product footprints and product passports will be mandatory. So that covers the second question. Oh, hopefully. Third question. Just the keyword, prices. Yes, thanks.
More options than
Yes.
price.
Also, their battery regulation is pretty neat. So the battery regulation mandates that producers that put a battery on the market, on the European market, need to show that for 4 materials, lithium, cobalt, nickel, and lead, they fulfill a minimum requirement of secondary materials. There, unfortunately, fabrication waste is still okay. Unfortunately, so this is imperfect, but there is a minimum requirement. If you're under that, you cannot put it on the European market, if it's actually lived that way. But that's current law, and it's in force. So that was accepted. So in a few years, after some transition period, this will be mandatory. Even if it's a Chinese battery, even if it's a US battery coming from the Inflation Reduction Act, they will have to show that they have, for lithium, 12% recycled material. Now come the systems perspective once again. We don't actually know if those 12% material are available on the market. If everyone would have to fulfill that with this drastically increasing demand, it might not be possible to actually recycle as much material to get to those 12% for all products that are put on the European market. In those cases, maybe then the ambition level might go down, but that's currently the ambition level. You need to fulfill ever-increasing recycling rates. So this is a buy green regulation, which is not market-based, which is not tax-based. It's just you have to fulfill this. The second large one, very similar to that, is by saying, oh, this product needs to be below this carbon footprint. And most producers currently go that way. Well, we can't actually further decarbonize because we have already purchased green electricity everywhere and we don't use natural gas anymore. So all of our footprint is scope 3 from materials that we scope. So we mandate that our supplier gives us a product which has 80% recycled material. All of this needs to be green steel, etc. And currently the suppliers say, yeah, we will do that. Will be tricky to follow up on that, and there will be a lot of lawsuits where this will not be fulfilled. But this is also carbon taxation and carbon footprinting, mandating that the carbon footprint needs to be lower than a specific threshold will mean that the OEMs will look much more into, is my material also green? And recycled materials are typically much lower, come with a much lower carbon footprint than primary materials, so this will be a lever.
Okay, hi Christoph, thanks. I have basically a follow-up question maybe to Hansi's second question. So we talked a lot about technological options for increasing the duration, the lifetime of metal elements staying in the anthropogenic cycles. Mm-hmm. And I was wondering what's the human dimension in there. So like for instance now in these losses in collection and so on, like is there a substantial contribution from losses through human behavior, for instance, just throwing trash away or keeping the smartphones in the drawer? And then also, could this be like a lever in the future to, for instance, have less tax on labor to kind of, yeah, then have more people cheaply repairing stuff and maybe even with a laser scanner, like disassembling products to even be better recyclable, something that machines cannot do at the moment.
Yeah. All right. Yes, there is a human component specifically for electronics. So for consumer electronics don't belong into the waste bin, into your household waste, municipal solid waste, ever. Full stop. No matter how large the product is, unless maybe it's some kind of a medical device, okay, then it might be something more tricky, but it doesn't belong in there. And it's for consumer electronics, it's partially a human, partially a societal challenge to organize then the take-back mechanisms through other ways, because it simply doesn't belong into that part, because the materials will typically be lost, because if you incinerate that once, well, that doesn't work. And sorting of materials, well, before waste incineration, that typically doesn't work. So because we basically put all our municipal solid waste through waste incineration in Central Europe, therefore this is quite a bit of a challenge to get people to actually really do that. Smartphones in your drawer, from the statistics that I have, not that much of an issue anymore. Yes, it has been a problem, but now with these take-back mechanisms, and you actually get a lot of deducts if you actually send back your phone, and smartphone use times having increased actually from about 3 years on average to about 4.5 years on average now. People actually use their phones longer, so apparently there has been some shift. Therefore, this is apparently not that much of an issue anymore. And last part of that question was?
Well, whether this could be like a lever in the future to, have like more people have jobs in repair.
The repairing, yes. Yes. I probably can't answer this question properly, because there's this typical answer of like, well, if you tax work less, then people will have more efforts in that, but I don't have any data on that. I'm not working on how people actually work in terms of, so as soon as humans come into play, not machines, then typically my job stopped. Most of these metals are recycled.
That's also an important part, to know when to not answer anymore, or where your expertise ends. So we have one last question in the chat before I would like to close, which is how substitution and reduction decisions on the demand side could affect specific metals and the critical raw materials landscape in general. So I would think this is about how much can we do regarding demand side measures, but as also substitution.
Yeah, demand side measures.
We talked about it today a little bit from Tom Gradle's work, that some
demand side measures tricky. Substitution measures and efforts a lot, because if there's a substitute available in practice, it changes the market drastically. So there's a side story, once again on the battery side. So apparently the CATL boss, the CEO of CATL, which is the largest battery producer in the world, Chinese company, has said in a meeting that they invented LFP batteries just because they were rid of their suppliers giving them higher prices every year. So just the availability that there are LFP batteries available that don't use nickel, that don't use cobalt in there, has reduced nickel and cobalt prices by a factor of 5. Now LFP batteries are not competitive anymore because lithium-ion batteries are also cheap, once again. But I mean, they do have a second option still in the market, and they can always say, well, if you raise the prices again, we'll just go back to the LFP because we have it now fully developed. So we do actually have something to negotiate with. And that also, of course, means that this is highly flexible in terms of, well, if really lithium would become, well, lithium is the wrong example because all of these lithium-ion batteries require lithium. If really there's a nickel shortage or a cobalt shortage, the market can now shift away to LFP batteries. So therefore also, well, it's not that you're only reliant on Chinese cobalt. Oh, you might just use Chinese phosphate instead. But of course, then regarding the single material, you're less reliant, and this material is less critical.
Okay, thank you very much. If there is no further pressing questions, I would like to end with a round of applause for the great talk.